Good day, everyone. So, my topic is about the Hellenistic mathematics. So, the Hellenistic mathematics started in the 3rd century by the wake of the conquest of Alexander the Great. So, during this time, the mathematical breakthrough were also the beginning of the Hellenistic Empire. So, it started from the crowning of Alexander to the death of Cleopatra. So this all happened in the place in Alexandria. So Alexandria, this is the great center of learning under the beneficent rule of the Ptolemies. So here there is a famous library that gained the reputation to rival that of the Athenian Academy. So the patron of this library was the first professional scientist paid for the devotion to research. So that was Alexander the Great. So among the best known and the most influential mathematicians that studied in Alexandria are Euclid, Archimedes, Eratosthenes, Heron, Menelaus, and Diophantus. So those are the famous contributors during the Hellenistic mathematics. Okay, so let's start with the contribution of Euclid. So who is Euclid? So Euclid, he is known as the father of geometry. So one of the famous book that was written or wrote by Euclid was the Stoichon or the Elements. This has 13 chapters, which represents the culmination of mathematical evolution in Greece. So what was the book Elements all about? So it is the set for all time, the model for mathematical argument following logical deduction from initial assumption in order to establish proven theorems. So what are these called the logical or the initial assumptions? These are what is known now as the axioms and the postulates. So element was also a lucid comprehensive compilation of the explanation of of all the known mathematics of his time. So the discoveries of the different concepts of mathematics, including the work of Pythagoras, Hippocrates, Thaddeus, Titius, and Exodus. Okay. So let's start discussing the five general axioms. So the first axiom states that things which are equal to the same thing are equal to each other. So what is this all about? So let's say for example we have A that is equal to B and B is equal to C. Therefore, if A is equal to B, then B is equal to C. Therefore, we have A that is also equal to C. If you will refer this to the latest concept of mathematics right now, that is what we call the transitive property of the equality. So another is if equals are added to equals, the whole or the sums are equals. So therefore, if we have A plus B is equal to C, then D plus E, which is also equal to C. Therefore, we have A plus B, which is equal to D plus E. Okay, so another, if equals are subtracted from equals, then the remainders are equal. So therefore, ato lang siyang i-replace. So let us just replace A minus B, which is A minus B, which is equal to B, C. Then we have D minus E, which is also equal to C. Therefore, A minus D is also equal to, A minus B is equal to D minus E. Then another, if things that coincide with one another are equal to one another. So therefore, if we have two figures here, a triangle for example, which is equal to the same triangle, given that they have the same angle, the same sides. Therefore, if we will overlap these two figures, we will get two overlapping figures which coincide with one another. And the last action we have here, the whole is greater than the part. Then it is obvious that if we have a circle here, if we will have a cut here of the portion of the circle, it is obvious that the whole, or we have figure A, is all is greater than the part of it. So let's say for example we have 1/4 here. So it is obvious that one whole is equal to, oh no, is greater than, no, not equal, greater than 1/4. Okay, so let's move now to the next postulate. Oh, okay, to the 5 geometrical postulates. So on the 5 geometrical postulates, the first one, it is possible to draw a line from one point to any point. So let's say for example we have point A here and another point B here. If we will draw a line here, it is possible that we will draw a line from A to B by simply connecting. Then for the second postulate, it is possible to extend the finite line continuously in the straight line. So given that we have here two points with lines are connected to each other, it is possible to extend another line here, extending our given line. Okay. Then the third one, it is possible to create a circle with any center and distance. So let's say for example, okay, so the area of our circle always depend on the radius. So let's say for example we have radius 3 here. So it is obvious that the circle with radius 5 is bigger than it. So it is possible to create with any center and distance. So the distance here is referred to the radius of the given circle. Next, for the fourth one, all right angles are equal to one another. So it is obvious that if we have a right angle here, no matter what where it is facing, though they are all equal, since all right angles, or the measure of a right angle is equal to 90 degrees. So we don't have to argue about this. Then if a straight line crossing two straight line makes the interior angle on the same side less than two right angles. So what is the measure of two right angles? If we have two right angles, that is 180 degrees. So therefore, if we have two parallel lines here and we will draw another straight line or a transversal line here, we will create, or we will be forming two interior angles that are less than 180 degrees. Okay, so among the many other mathematical gems on the 13th volume, so on the 13th volume of Elements contain the formula for calculating the volume of a solid, such as cones, pyramids, and cylinders. Also, included in the book of Elements was the proof about the geometric series, the perfect numbers and primes, the algorithm in finding the greatest common divisor, and least common multiple of two numbers. So another was the proof of Pythagoras theorem. So the proof were the infinite number of Pythagoras triple. And the final definitive proof that there can be only 5 possible regular Platonic solids. Okay, so let's discuss here the Pythagoras theorem, the Euclid's proof of Pythagoras theorem. So it revolves around the fact that if you will draw a right triangle from the right triangle, okay, so we have here a right triangle, this one, meaning have a figure inside. Okay, so if we will draw another perpendicular line that will from point E down to the side BD, I mean BC. So therefore we will form two triangle now. So it is said that the If a line is drawn from the right angle perpendicular to the hypotenuse and down through the square on the hypotenuse, that square is split into two rectangles having the same areas on the square. So how many rectangles do we have now? If in the Pythagorean theorem, we have only three rectangles. So for the proof of Euclid on Pythagoras theorem, he added another triangle. So in this figure here, he stated that the area of this rectangle is equal to the area of, this is area 1 and is equal to this one. And the area of triangle 3 and triangle 4 are also equal. So that was the proof of Euclid on Pythagoras theorem. So the Pythagorean theorem can be used to find the length of any side of the right triangle. The opposite side of the triangle is called the hypotenuse. So this is the hypotenuse. Ato lang i-review magamay. So let us just have a recap of what is the Pythagorean theorem all about. So that is, if we will express the figure into the equation, the idea of Pythagoras, that is a squared plus b squared, which is equal to c squared. The Book of Elements also includes the series of theorems. So as stated earlier, they have there the we have the completed number. Wait. Okay, so on the Book of Element, we have the proof of geometric series, the perfect number, in primes algorithms. Okay, so let's move now. So the elements includes the series of theorems on the properties of numbers and integers, making the real beginning of the number theory. So let's for example, Euclid proved that what has known as the fundamental theorem of arithmetic of the unique factorization theorem, or that every positive integer greater than 1 can be written as the product of prime numbers. So example, we have 21. Okay, so this can be written, this one is written as 7 times 3. Then 113 is written as 1 times 113. So those are prime number. So but what about 1200? So we have 2 times 2. Okay. 1, 2, 3, 4 times 2 times 2 times 2. We have 2 times 5 times 3 times 5. Okay, so if we have 2, 2, therefore we have 1, 2, 3, 4, 5, 2 to the power of 5 times 5 squared times 3. So if you will do this mathematically, so we have 2 to the power of 5, that is 32, times, okay, we have 32 times 25 times 3. Okay, so times 25 times 3, so that is equal to, okay, nanubra daig 2. So we only have 2 to the power of 4. So that will be equal to 1,200. So another example, 6,936. That will be equal to how many? 2. 6,936 divide 2, 1, 2, 3. Okay, so we have 2 to the power of 3 times, divide 3, 1, 2, times 3 times 5, 7. No. Wait. 289 is not divisible by 3, 5, 7. Is it divisible by 11? So we have here 2 to the power of 3 times 17 squared. So we have 2 to the power of 3 times 3 times 17 squared. So we have 6,936. So that is the idea of Euclid, that all the numbers greater than 1 can be expressed as the prime factorization, or the factorization of prime number. Then he was also first to realize and prove that there are infinitely many prime numbers. So the basis of this proof was often known as Euclid's theorem. So is that for any given finite set of prime, if you will multiply all of them together and then add one, then a new prime has been added to the set. So let's say, for example, 2 times 3 times 5, that is equal to 30, plus 1, then that is equal to 31. So that 31 is a prime number. So another example. So let's give at least 3 prime number based on Euclid's theorem. So we have 2 times 3. No, we have 2 is done. So we have 3 times 5 times 7. So 3 times 5 times 7, that is equal to 105. That is equal to 105 plus 1. No, wait. There is something wrong in here. Okay, so going back, we will add 2 here. So we have 2 times 3 times 5 times 7. That is equal to 210. So it is said that if we will add 1 here, we will be creating, or we will be producing another prime number. So therefore, if we will add 1, we have 211. So therefore, 211 is a prime number. Okay, so another. Okay, so 2 times 3 times 5 times 7 times 11. Okay, so we have 2 times 3 times 5 times 7 times 11. That is equal to 2,310. Then if you will add 1, that is another prime number. So 2,311 is a prime number. Okay, so let's move now. Okay, Euclid also identified the first 4 perfect numbers. So what do you mean by perfect number? So a perfect number is that there are the numbers that are the sum of all their divisors. So let's say, for example, 6. What are the divisors of 6? We have 1, 2, and 3. If we will add 1, 2, 3, that will be equal to 6. What about 28? So 28, we have 1, 2, 2. What else? We have 4, 7. What else? 28 is divisible by 4. 28 is also divisible by 7. It is also divisible by 14. So if you will add this, 14 plus 7 plus 4 plus 2 plus 1, that is equal to 28. And the same will happen to the rest of the numbers. So you will try it by yourself 489 and 8,128. So he note that these numbers also have many interesting properties. So aside from adding their their divisor, summing up the divisor, it is also have another property. So they are triangular number, and therefore the sum of all the consecutive numbers adds up the largest prime factor. So therefore, so that was what has been explained earlier. So if you will add, that is the largest factor. So if you will add 1, 2, and 3, that is equal to 6, which is a divisor of 6. So their largest prime factor is a power of 2, 2 less than 1. So what does it mean? So if we have 2 here, 6 here, that is 2 to the power of 1 times 2, 2 squared minus 1, that is equal to 6. So for 28, we have 2 squared times 2 cubed minus 1, that is equal to 28. Okay. So Euclid also introduced the irrational square root of 2. So why is the square root of 2 irrational? See, here is the proof. Suppose that you have square root of 2 that is irrational. So that means that it can be written as a ratio of two integers p and q. So we may assume that p and q have no common factors. So if there are any common factor, we have to cancel them in the numerator and denominator. Squaring in 1 in both sides gives 2 is equal to, okay, since we have squared both sides here, squared, no, wait, if we will square both sides here, so that will give us 2 that is equal to p squared over q squared. So this implies that if we will cross multiply this one, we have p squared that is equal to 2q squared. And therefore, p squared is even. So the only way that this can be true is that p itself is even. Okay, so another contributor on the Hellenistic mathematics is Archimedes. So who is Archimedes? Okay. Archimedes was a Greek mathematician who also studied in Alexandria during the 3rd century BCE. So although he was born, died, and lived most of the life in Syracuse, a little of his known short life and many of the stories and anecdotes about him were written after his death by the historian of the ancient Rome. So also, Alexander, no, Archimedes is an engineer, an inventor, an astronomer, and he was best known throughout the most history for his lots of military innovation. So what are the contribution of Archimedes? So Archimedes produced the formula to calculate the area of regular shape. So using the revolutionary method of capturing new shapes by using shapes he already understood. So he was the one to produce the formula to calculate the areas of regular shapes. Another, he wait. Okay, so let's say for example, the area of the circle. So he constructed a large polygon outside of a circle and one on the smaller side. Okay. And another smaller circle inside of it. So wait. Okay, so let's say for example, Archimedes already know the area of a triangle. So he constructed a figure that he already know outside the circle. Okay, so that was his way of capturing or discovering the formula of a new shape using the shapes that he already understood. Okay. Then Euclid, he also calculated the approximate volume of a solid like sphere by slicing it up in a series of cylinder and adding up the volume of the constituents. Wait. Okay, so let's say for example, ani ang sphere ni ha, ball kunohan ni. Then he sliced this into small pieces. Oh no, thin slices. Then making the slices thinner as the slices of the sphere goes thinner, he got the approximation, the exact approximation of the volume of the given sphere or figure. Then another contribution of Archimedes was the quadrature of parabola using the method of exhaustion. So Archimedes' most sophisticated use of method of exhaustion, which remained unsurpassed until the development of integral calculus in the 17th century, was the proof known the quadrature of parabola. So this idea of Archimedes was proven on the later 17th century. So this was known now as the quadrature of the parabola, that the area of the parabolic segment is four-thirds that of the certain inscribed triangle. Okay, so this parabolic segment, okay, so in this in his idea, the area of this parabolic segment, that is four-thirds of the area of the triangle inscribed into it. Then another example of meticulous and precision of Archimedes was his calculation of the value of the square root of 3. So that was the approximation of Archimedes. Also, the discovery of which Archimedes claimed the most proud was that of the relation between a sphere and a circumscribing cylinder of the same height and diameter. So Archimedes showed that the volume and the surface area of the sphere are two-thirds of the circumscribing cylinder. So giving the formula we have now, times four-thirds times pi r cube. So that was the approximation of Archimedes. Okay, and maybe you are familiar of the anecdotal story of the discovery of the method in determining the volume of an object. So if you will remember the story, this happened to be funny story, or a ridiculous story. So while Archimedes was taking a bath on that day, he noticed that the level of water in the tub rose as he got in. So kung isya kanang ibutang ang iyang kamot inside the kanang basin or the pail, mo saka ang level sa water, and he had a sudden inspiration that he could use this effect to determine the volume. So given that mo rise mo saka ang level of the water, he make an assumption that this can be possible to determine this is the possible way of determining the volume of irregular solid. So let's say for example kanang mga bato, the stones, or even kanang figures that are irregular in shape. It's very difficult to determine the area of that. But because of this, so in his excitement, he apparently rushed out to the bath and ran naked through the street shouting, "Eureka! Eureka!" So Eureka means I found it, I found it. So this gave rise to what has become known as Archimedes' principle, that an object is immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. So mao na tong, for example, the level of the water here in this figure is naara sa 29 ml. Then inigbutang nimo sa stone, mahimo na siyang 28. Okay, so this water here nga ni displace or even imura ng i-minus ng ilang level of water that is equal to the volume of the irregular shape inside or put in the water. Okay. So, according to the legend, Archimedes was killed by the Roman soldier after he captured the city of Syracuse. So, he was contemplating a mathematical diagram in the sun and enraged the soldier by refusing to go to meet the Roman general until he had finished the work on the problem. His last word was, "Do not disturb my circle." So another famous mathematician was Diophantus. So what's Diophantus? Diophantus was a Hellenistic Greek mathematician who lived in Alexandria. So he is sometimes called the father of algebra and wrote the influential series of book called Arithmetica. So what is this Arithmetica? Arithmetica is a collection of algebraic problems which greatly influenced the subsequent development of the number theory. Okay, so what was the contribution of Diophantus? So he was the first to recognize fraction as a number and is considered as the early innovator in the field of what was later become known as algebra. So matong gitawag siya as the father of algebra. So another, he applied himself to some quite complex algebraic problem, including what is known now as the Diophantine analysis, which deal in finding the solution to the kind of problem that lead to equation of several unknown. Okay, so let's see for example, we have 25x is equal to plus 95y is equal to 970. So how are we going to solve this one using the idea of Diophantus? So first one, we have to identify the GCD of the number. So what is the GCD of the number? So we have 25 and 95. So what is the GCD of the number? 95, that is equal to 3 times 25 plus the remainder, which is 20. Then 25, that is equal to 1 times 20 plus the remainder, which is 5. Then 20, that is equal to 4 times 5, then 0 with the remainder of 0. So therefore, our GCD here is 5. So since we have GCD, we have to prove that the GCD 5 divides the number 970 here kani. So dapat ang atong GCD must divide 970. So from the given, we have our GCD which is equal to 5. Then 5 divides 970. So therefore, there is a solution for the given equation. So to find the solution, we have to express the GCD of 25 and 95 as a linear combination of 25 and 95. So now we have 5. Since our remainder or our GCD is 5, so therefore we have 5 that is equal to 1 times 25 minus 20 times 1. Then 5 is equal to 1 times 25. Then what is 20 times 1? That is 1 minus 1 times 95. Kalisod ba magsuwat ani? Oy, minus 3 times 25. Then we have 5 is equal to 1 times 25. Na naman tayo 25 no? Here, na tayo 25. So, di na nato labtan. So, 1 and 25. No, we have now, ang ato ni siyang ikuan, that is, that is now, positive 3. Kay minus man ni si Jam. So we have positive 3 now. So we have 4 times 25 minus 1 times 95. So therefore, our solution is equal, x is equal to 4 and y is equal to negative 1. Then after that, since we have 9 which is equal to 4, uh, wait. So going back, we have x which is equal to 4 and y which is equal to negative 1. So this is our A, our B, and our C. And our D is equal to the LCD, the greatest common factor, which is 5. We have to find E, where C is equal to D times E. Our C is 970 and our D is 5, which is our GCD and E. So therefore, times E, our E now is equal to 194. Okay. So hence, our E is equal to 194. Going back. Okay, we have E equal to 194. So if we will multiply 194 times 5 here, which is the GCD, times 25, the last part of 25 times 4 plus 95 times negative 1. Therefore, we have 970 is equal to 25 times ato ning i-multiply diri 776 and plus 95 times ato ning ikuan multiply diri negative 194. Therefore, the solutions of the given are x is equal to 776 and y is equal to negative 194. So that is the way of solving or doing the Diophantine equation. Okay. So one of the problem that was from the later 5th century, the Greek anthology of number games is sometimes considered to be Diophantus' epitaph. So here lies Diophantus. God gave him his boyhood 1/6 of his life, 1/12 more as youth, while whiskers grow rife. And then yet 1/7 ere marriage begun. In 5 years there came a bouncing new son. Alas, the dear child of master and sage, after attaining half of the measure of his father's life, chill fate took him. After concealing his fate by the signs of numbers for 4 years, he ended his life. Okay, the puzzle implies that the Diophantus lived to be 84 years old, all through its biographical accuracy is although his biographical accuracy is uncertain. Ay, kalisod. Okay, so another contributor, though they don't have much in their contribution, but another is Eratosthenes. So Eratosthenes introduced us the sieve of Eratosthenes, which which helps us identify the prime numbers. So this one here, this is how are we going to apply it to find the prime numbers up to any value. Okay. So another was Heron. So Heron was a great inventor and best known in the mathematical circles of Heronian triangles. So he was best known of what is known now as Heron's formula. So what is the Heron's formula? So that is S is equal to A plus B plus C. This is used in determining the area of a regular triangle given the sides and the area that is equal to the square root of s times s minus a times s minus b times s minus c. So, square root na silang tanan. Okay. Then, another is Menelaus. So, Menelaus was known for his book that dealt spherical, which dealt with the geometry of spheres and its application in astronomical measurement and calculation, and introduced the concept of spherical triangle, a figure formed of the great circles and arc. Then another is Hypatia. Hypatia was the first recorded female mathematician, and he is a renowned teacher who had written some respects commentaries on Diophantus and Apollonius. She was dragged to her death by the Christian mob in 415 after death. Okay, so let's move now to the Roman mathematics. So, the Roman mathematics was started by the middle of the 1st century before Christ. The Romans have tightened their grip on the old Greek and Hellenistic empire, and the mathematical revolution of the Greek ground to halt. So, despite of their advances in other respects, no mathematical innovation occurred under the Roman Empire and Republic, and there were no mathematicians of note. So the Roman had no use of pure mathematics, so only for this practical application and the Christian regime that followed it. Then, the only known mathematical concept that was developed during this time was the Roman numeral. So that is known today and were the dominant number system for trade and administration in most of Europe for the best part of the millennium. So this is the Roman numeral. So under the Roman numeral, they have value for 1, 5, 10, 50, 100, 500, and 1,000. So let's say for example, we will write 1,944. So for 1,000, we have 1M. Then for 500, we have D. For another 400, we have 4C. And then 400, we have 4. Then since the subtractive method was applied during this time, so instead of writing dominant numbers of the letters, we can write this using the subtractive method. So we have MCM, MCM, XL, IV. So that is the one here. So what is the subtractive method? So those that are written on the left can be subtractive. So therefore, if we have 900, we can write this as CM. So we're subtracting 100 from 1,000. Okay, so another, we have the Mayan mathematics. So the Mayan mathematics. Okay, so also there are no much development. So the Mayan civilization settled in the region of Central America. Then its peak was one of the most densely populated and culturally dynamic societies in the world. The importance of astronomy and the calendar calculation in Mayan society required mathematics. Like the Roman, they have representation of the different numbers. So let's see, this is the Mayan numeral. So for 0, they have shell, and 1 dot, then 2 dot, 3 dot, 4 dot, yan nila. Then kung mo 5 na, they will draw 1 bar to represent 5. But, for example, moabot na og 20 because this is on the base of 20. So, kung moabot na og 20, for example, they will draw 1 dot here. Isod sa box nato ha. So, kintahay 20 diri at 21. So they will draw one box here. This is for 20 and another box here. So that is 21. Kung duha, 22. Kung butangan na ni mag-line diha, that is 27. So, the Mayan arithmetic, so 28 is equal to 1 times 20. So, since we have mo na itong kuhan ganina, this can be counted as 20 plus 5 and tulo ka 1 here. So, we have 28. Then, I guess that will be the end of my topic. So, thank you for listening, watching. God bless.